Imagine standing on the surface of our world 4.5 billion years ago. You would not recognize this place. There are no blue oceans, no green canopies, and no breathable air. Instead, you are standing inside a furnace. This is Earth during the Hadean Aeon, a name appropriately derived from Hades, the Greek god of the underworld. It was a planet defined by fire, a blazing sphere of molten rock churning under the violent chaos of the early solar system. At this embryonic stage, Earth was not a home. It was a hostile exclusion zone. The surface was a glowing, viscous ocean of magma, constantly torn apart by the impacts of asteroids and comets left over from the formation of the planets. This was the era of the Late Heavy Bombardment, a celestial assault occurring roughly 4.1 to 3.8 billion years ago, where the heavens rained destruction upon the young world with terrifying frequency. Solar radiation, far stronger and more volatile than what we experience today, scorched the planet, stripping away any semblance of stability. The atmosphere itself was a lethal cocktail, a reducing mixture composed of carbon dioxide, methane, ammonia, and hydrogen sulfide. It was a sky of toxic smog, likely glowing with an eerie orange or pink hue, utterly devoid of free oxygen. To a modern human, a single breath of this primordial air would be instantly fatal. Yet it is within this chaotic, sterilized hellscape that the most profound miracle in the universe took place. Life did not just survive here, it was forged here. But before biology could begin, geology had to settle. The first great transformation was the cooling of the crust. We know this thanks to the most resilient time capsules on Earth. Zircon crystals. Discovered in the Jack Hills of Australia, these microscopic minerals have been dated to approximately 4.4 billion years ago. Their existence tells us something extraordinary, that even in the Hadean inferno, parts of the planet's skin had cooled enough to solidify, and perhaps more shockingly, to support liquid water. This begs a fundamental question. Where did the water come from on a world that was once a sea of fire? While comets likely delivered some moisture from the frozen outer reaches of the solar system, modern science suggests that the bulk of Earth's water was born from within. As the planet cooled, the magma oceans released vast quantities of trapped water vapor through a process called internal degassing. This vapor rose, condensed in the cooling atmosphere, and fell as torrential rains that lasted for millions of years, eventually drowning the fire to create the first global oceans. The transition from the Hadean to the Archean Aeon, around 4.0 billion years ago, marked the stabilization of this water world. However, the oceans of the Archean were not the clear blue expanses we know today. They were dark, heavy with dissolved iron, and warmer than a tropical bath. Without oxygen to rust the iron, the seas likely appeared green or black, churning under a sky that blocked out the stars. In this alien darkness, chemistry began to cross the threshold into biology. Geochemical evidence found in the ancient sedimentary rocks of Greenland and Canada reveals curious carbon signatures, specifically, an unusual ratio of carbon-12 to carbon-13, dating back 3.8 billion years. This is the chemical fingerprint of life, as biological processes prefer the lighter carbon-12 isotope. But where could it have started? The surface was still bathed in lethal ultraviolet radiation, as there was no ozone layer to shield it. Any organic molecule exposed to the sun would have been destroyed instantly. Therefore, life did not look up to the stars. It looked down into the abyss. The prevailing scientific consensus places the cradle of life on the floor of the deep ocean, around hydrothermal vents. Here, seawater seeps deep into the fractured crust, reacts with superheated, metal-rich rocks, and erupts back into the ocean as mineral-laden fluids. These white smokers and black smokers provided everything a nascent organism needed: thermal energy, is catalytic minerals, and chemical gradients. In these pitch-black depths, the first life forms did not photosynthesize, they chemosynthesized. They were simple, single-celled organisms, likely bacteria and archaea, that fed on the chemical energy of the Earth itself. They metabolized hydrogen, sulfur, and iron, thriving in conditions of crushing pressure and boiling temperatures, environments that would sterilize a modern human operating room. This era brings us to the RNA world hypothesis. Before the complex double helix of DNA and the sophisticated machinery of proteins took over, it is believed that RNA molecules ruled. These versatile strands could both store genetic information and catalyze chemical reactions, serving as the bridge between non-living matter and the first true cells. It was a biological singularity, and a moment where dead matter learned to replicate. The survival strategy of these early organisms was one of avoidance and endurance. They were anaerobes, living in a world without oxygen. In fact, oxygen would have been toxic to them, a corrosive poison capable of dismantling their molecular bonds. They were the masters of the dark, hiding beneath the water which acted as a natural shield against the sun's radiation. This allowed their fragile molecular structures to persist, replicate, and slowly evolve. One of the most tangible records of this ancient struggle is found in stromatolites. These are not individual creatures, but microbial cities, layered, rock-like structures built by colonies of microorganisms. By trapping sediments and binding minerals, these microbes built high-rise apartments of stone, layer by microscopic layer. The oldest known stromatolites date back 3.5 billion years, and in a testament to life's tenacity, their descendants still exist today in places like Shark Bay, Australia. They are living fossils, a direct link to a time when the only life on Earth was a microscopic slime coating the rocks of a hot, toxic sea. For hundreds of millions of years, this was the status quo. The Earth was a quiet, microbial planet. Evolution moved at a glacial pace, dictated by the slow rhythm of geology and the subtle exchanges of chemistry. Life was confined to the microscopic, trapped in the safety of the oceans, feeding on the heat of the planet's core. But this stability was a ticking clock. Deep within the genetic code of some of these organisms, as a new biological machinery was being assembled, a mechanism that would tap into the ultimate power source of the solar system. It was a mutation that would unlock the energy of the sun, and in doing so, unleash a waste product so reactive, so destructive, and so transformative that it would nearly wipe out all life on Earth. The stage was being set for the first global apocalypse and the subsequent rise of a new world order. The Hadean fire had cooled, and the Archean darkness was filled with life, but the atmosphere remained a suffocating blanket. The planet was waiting for a breath of fresh air, unaware that the very act of breathing would trigger a catastrophe of ice and extinction. The era of the deep dark was ending. The age of light and oxygen was about to begin. Around 2.7 billion years ago, the Earth's trajectory was permanently altered by a microscopic biological accident. In the warm, iron-rich oceans, a specific group of single-celled organisms, the cyanobacteria, stumbled upon a new way to survive. They did not scavenge for scarce chemical nutrients in the dark. Instead, they turned their faces to the surface and tapped into the most abundant energy source in the solar system: sunlight. Through the process of photosynthesis, these organisms use solar energy to split water molecules, consuming carbon dioxide and releasing a waste product that the planet had never truly known before: molecular oxygen. At first, this gas did not accumulate in the atmosphere. Instead, it was immediately consumed by the chemistry of the oceans. The seas were saturated with dissolved iron, and as the oxygen met the iron, it triggered a planetary-scale chemical reaction. The oceans began to rust. Insoluble iron oxides rained down onto the seafloor like red snow. settling into vast layers that we see today as banded iron formations. These geological scars, concentrated between 2.4 and 2.0 billion years ago, are the direct evidence of a world bleeding out its old chemistry. But once the iron sponge was full, the oxygen had nowhere left to go but up. It burst from the oceans and flooded the atmosphere, triggering the Great Oxidation Event. To us, oxygen is the breath of life. To the anaerobic organisms that had ruled Earth for over 1 billion years, it was a corrosive, lethal poison. As oxygen levels rose, it tore apart the metabolic machinery of the ancient microbes. This was the first mass extinction in Earth's history, a silent holocaust where the vast majority of life on the planet was wiped out, leaving only those who could adapt to this harsh, oxidizing new world. But the oxygen revolution did more than kill. It destabilized the climate. For eons, the Earth had been kept warm by a blanket of methane, a greenhouse gas roughly 30 times more potent than carbon dioxide. As oxygen filled the air, it reacted with the methane, breaking it down and stripping away the planet's thermal insulation. The global temperature plummeted. The Earth entered a catastrophic feedback loop. As ice sheets expanded from the poles, the albedo effect took hold. The white ice reflected sunlight back into space far more efficiently than the dark oceans or land, causing the planet to lose even more heat. This cooling triggered more ice, which reflected more sunlight, and spiraling the world into a deep freeze. This was the cryogenian period, the era of snowball Earth. Between 720 and 635 million years ago, the planet was transformed into a solid ball of ice. Glaciers stretched from the poles all the way to the equator. The oceans were sealed beneath ice sheets estimated to be nearly 1 kilometer thick. The hydrological cycle slowed to a crawl. The surface was a dead world, silent, frozen, and white. To an outside observer, Earth would have appeared indistinguishable from a lifeless moon. Yet, life is stubborn. Beneath the crushing weight of the ice, in the eternal darkness of the deep ocean, the hydrothermal vents continued to pump out heat and chemicals. In these isolated oases, and perhaps in small cracks in the ice where faint sunlight could penetrate, the remnants of life held on. For millions of years, evolution was confined to these cramped refuges, waiting for the siege to end. The liberation came from below. While the surface was frozen, the Earth's tectonic engine never stopped. Volcanoes continued to erupt, punching through the ice and spewing carbon dioxide into the atmosphere. With no liquid rain to wash the CO2 out of the air, a process known as silicate weathering, the gas accumulated over millions of years. Eventually, the greenhouse effect roared back to life, trapping heat and triggering a rapid, violent melt. As the ice retreated, it ground against the continents, pulverizing rock into mineral-rich dust. When the glaciers finally melted, they flushed a massive pulse of nutrients, phosphates, nitrates, and iron, into the oceans. The seas, now warm, oxygen-rich, and flooded with fertilizer, had become a cradle for the greatest biological explosion in history. Life did not just return, it detonated. Around 541 million years ago, the Cambrian explosion unfolded. In a geological blink of an eye, a mere 20 to 30 million years, evolution accelerated at a pace never seen before or since. The fossil record, previously marked by simple bacterial mats and soft-bodied oddities, was suddenly crowded with complex, multicellular animals. Nearly every major animal phylum we recognize today appeared during this window. Arthropods, mollusks, segmented worms, and the early ancestors of vertebrates. But the Cambrian was not just about diversity. It was about the invention of warfare. Before this, life was largely passive. Organisms absorbed nutrients from the water or grazed on microbial mats. In the Cambrian, life learned to hunt. Yet this new ecological pressure forced a revolutionary change in biological architecture, the development of hard parts. To survive a world of predators, prey species evolved mineralized shells, spines, and primitive armor. In response, predators developed grasping claws, crushing mouthparts, and, perhaps most profoundly, eyes. The invention of the eye transformed the rules of survival. For the first time, life was not just chemically sensing its environment, it was watching it. The cloudy, instinctual world of the past was replaced by a world of sharp visual acuity, where a shadow passing overhead meant death. Fossil evidence shows that primitive visual systems emerged very early in the Cambrian, sparking an evolutionary arms race that drove species to become faster, harder, and smarter. The oceans became a theater of monsters. Creatures like Anomalocaris, a bizarre apex predator, patrolled the seas with grasping limbs and a circular mouth lined with teeth. The seafloor crawled with trilobites, heavily armored arthropods that would dominate the oceans for millions of years. The Burgess Shale fossils reveal even stranger experiments: organisms with 5 eyes, asymmetrical bodies, and tubular trunks, biological designs that look like hallucinations compared to modern life. Many of these forms were evolutionary dead ends, failed experiments in the chaotic laboratory of the Cambrian. Modern science suggests this explosion was driven by a convergence of factors. Oxygen levels had finally reached a threshold high enough to support the metabolic demands of large, active bodies. The development of collagen, the protein glue that holds cells together, allowed for complex structures. And the ecological vacuum left by the snowball Earth thaw provided an open canvas for innovation. However, this burst of creativity established a new, brutal reality. The Garden of Eden was over. Ecosystems were now defined by complex food webs, competition, and predation. Diversity did not guarantee durability, it only increased the stakes. The ocean was crowded, dangerous, and highly competitive. As the Cambrian seas teemed with life, the pressure to find new territories grew. Some organisms began to turn their gaze away from the water, toward a frontier that was harsher, drier, but entirely unclaimed. The continents were still barren rock, scoured by wind and radiation, but they held a promise of space. But the story of life was about to leave the cradle of the ocean and attempt the impossible, the conquest of the land. But to survive there, life would need to solve the problem of gravity, dehydration, and the direct, unshielded glare of the sun. The era of the waterborne was peaking. The era of the landborne was about to begin. While the oceans were a crowded theater of predation, the continents remained a silent fortress of barren stone. For billions of years, the land was a hostile realm of radiation and dust, where nothing lived. But around 470 million years ago, the first pioneers began to breach the shoreline. These were not animals, but plants. Simple, non-vascular forms resembling modern mosses that clung to the damp edges of the water, tethered to the moisture they needed to reproduce. Yet this botanical conquest did more than just decorate the rocks. It fundamentally re-engineered the planet. As plants spread, their roots broke down stone into soil, creating a sponge that held water and nutrients. They exhaled oxygen in vast quantities, pushing atmospheric levels far beyond modern concentrations. This surge in oxygen set the stage for the rise of giants. During the Carboniferous period, oxygen levels soared to an estimated 35%, compared to just 21% today. This hyper-oxygenated atmosphere allowed arthropods, limited by inefficient respiratory systems, to grow to nightmarish proportions. The skies were patrolled by meganeura, dragonflies with wingspans rivaling eagles. The forest floor crawled with arthropleura, millipedes the size of automobiles. It was a world of monsters, fueled by the very air they breathed. But the true conquest of land required a physiological revolution. Fish, driven by competition or drying pools, began to haul themselves onto the mud. They evolved fleshy, lobed fins, the precursors to our own arms and legs. These first amphibians were creatures of two worlds, able to breathe air, yet still shackled to the water for reproduction. Their eggs, soft and jelly-like, would dry out and die on land. To truly sever ties with the ocean, life needed to carry the water within itself. The breakthrough was the amniotic egg. With a hard, protective shell and a self-contained life support system, reptiles broke the final link to the sea. They could venture into the dry interior, colonizing deserts and mountains. This innovation sparked a biological arms race that would eventually lead to the most famous dynasty in Earth's history. The dinosaurs. For 160 million years, dinosaurs dominated the planet. They were not the sluggish, tail-dragging lizards of early imagination, but active, dynamic biological machines that filled every ecological niche. They were the masters of a world that was constantly changing, surviving shifting continents and fluctuating climates. But their reign was built on a fragility they could not foresee. 66 million years ago, a rock the size of a mountain, traveling at 40,000 miles per hour, slammed into what is now the Yucatan Peninsula. The impact released more energy than 1 billion nuclear bombs. In seconds, the Mesozoic era ended. A wall of fire consumed the Americas, and a cloud of dust and sulfur choked the sun for years. Photosynthesis stopped. Food chains collapsed. The giants starved in the dark. But in the ashes of this apocalypse, something small stirred. Mammals, which had spent millions of years scurrying in the ecological shadows of dinosaurs, suddenly found themselves in a world without masters. They were small, nocturnal, and unassuming, but they possessed a secret weapon: warm blood and complex brains. With the dinosaurs gone, mammals exploded into the vacuum. They grew larger, returned to the oceans as whales, and took to the skies as bats. But one lineage remained in the trees, developing grasping hands, stereoscopic vision, and social complexity. These were the primates. As the climate cooled and the African forests fragmented into savannas around 6 million years ago, then some of these primates were forced to the ground. They stood up. Bipedalism was a dangerous gamble. It made them slow and exposed their vital organs, but it freed their hands. They could carry food, wield tools, and gesture. But the most expensive adaptation was the brain. The human brain is a metabolic luxury, consuming 20% of the body's energy while representing only 2% of its weight. It required a high-quality diet and a long, vulnerable childhood where knowledge could be passed down. This was the birth of culture. We are the only species that has ever attempted to reconstruct its own history. When we look back at the 4.5 billion years of struggle, from the magma oceans of the Hadean to the frozen silence of snowball Earth, from the alien explosion of the Cambrian to the asteroid that cleared the path for us, we realize something profound. Our existence is not inevitable. It is a statistical improbability. If the asteroid had arrived 30 minutes later, it might have landed in the deep ocean, sparing the dinosaurs and leaving mammals in the shadows. If oxygen levels hadn't risen, complex life might never have ignited. We are the survivors of a billion-year gauntlet, the inheritors of a planet shaped by catastrophe. The geological record is a book of lessons written in stone. It tells us that dominance is temporary. The trilobites ruled for 270 million years. They are gone. The dinosaurs ruled for 160 million. They are gone. We have been here for a mere 300,000 years. We are now the first species capable of altering the biosphere on a geological scale. We have become a force of nature comparable to the asteroid itself. The carbon we release, the forests we clear, and the species we extinguish are writing a new layer in the rock record, the Anthropocene. Understanding prehistoric Earth is not just about satisfying curiosity. It is a warning. The planet has survived fire, ice, and impact. It will survive us. The question is not whether life will continue, but whether we will be part of it. The journey from molten rock to the thinking mind has been long and fraught with peril. It is now our responsibility to ensure that the light of consciousness, ignited against such impossible odds, does not flicker out in the dark.